Get it? All right, I will begin. Heavenly Father, we thank you for this day. Thank you for these students, for the weekend that's about to start. I pray that you'd help us use this time wisely, Lord. In your name I pray. Amen. We are now to lecture 27, which is on divisibility in integral domains. Part 1. Ooh. I mean, there would be a sequel to this, apparently. Very exciting. All right, so let us begin with a definition. Here it is. Let D be an integral domain. And let A and B be elements of D. Then we have the following choices. A and B are associates if there exists a unit U in D for which fine. If there exists a unit U in D such that B is equal to AU, I'm about to erase. It's not a duplication there. I have this bad habit of making my definitions go too far, and then when I write the theorem here, I get squeezed. So if I actually plan ahead, there we go. So that's associates. 2, A is an irreducible. All right, if A is not a unit, and whenever A is equal to CD, then C or D is a unit. Three, A with, well, let's say A not equal to A not equal to 0 is prime if A is not a unit and A divides BC implies A divides B or A divides C. Let me just take a moment to review what divides by means. So what's A divides BC mean in the context of a ring here? This means that there exists J in the ring, right? J and D such that what? BC is equal to what? JA, right? What's this mean? There exists K in the ring in the integral domain D such that what? B is equal to KD, KA rather. And A divides C, of course, means that there exists an L in the domain such that C is equal to La. Of course, you could say AK or AL or AJ because we're in a commutative ring, right? Integral domain is a commutative ring with no zero divisors. That's our context here, right? So we have these three kinds of terms we can talk about in association with elements. Two elements being associates, right? Or a given element either being irreducible or prime. And we'd like to study these terms and see how they play out. Notice that this terminology at least agrees in part 2 with our usage of irreducible polynomial last time, right? An irreducible polynomial is an irreducible element of the polynomial ring f of x, which, by the way, is an integral domain, right? Okay. But we have now left the narrow confines of polynomial rings, and we're looking at more general ring theory, right? I'm not assuming that D is a polynomial ring. So let's begin with an example, actually. And so this example is a special case of general class of examples, which is Z adjoin the square root of D, where D is square free. A lot of our examples come from things like this. We'll look at the case D equals to minus 3 for this example. So our integral domain we're going to look at is D is equal to Z adjoin the square root of minus 3. All right. You could view this as a excuse me, as a subring of the complex numbers, right? If you wanted to. And so what I want to look at then, in specifically, is the following bit of algebra. We're going to study 1 plus the square root of minus 3. This is a particular element of Z adjoin the square root of minus 3, right? And I want to argue that this is a prime. Well, excuse me, this is not prime, actually. What is it?
Is it minus square root of 3 or square root of 3?
Oh, that's a typo. Yeah, sorry about that. Good news is I was mostly right. What is it? Typo? Oh, yeah. What should I call it? A righto? I mean, all right. So, all right. So, I won't show this at the moment, but comment. If you look at 1 plus the square root of minus 3 equal to xy, for xy, in Z adjoin square root of minus 3, then this will imply that either x or y is a unit. So what does that mean? So I don't want to give you the details right now, but we can prove, I mean I will before the class is over, but we'll soon prove that in fact that is a what? What does that mean if what I wrote in blue is true? Right here, right? So we're saying that it's a product of two things, x and y, and either x or y is a unit. That is to say that 1 plus the square root of minus 3 is an irreducible in this ring. What I want to now argue for you is that 1 plus the square root of minus 3 is not prime. All right? So let's work it out. It involves the following steps. So we look at 1 plus the square root of minus 3 times 1 minus this, 1 minus the square root of minus 3, right? And that, of course, gives us 1 minus a minus 3, otherwise known as 4, which, by the way, is equal to 2 times 2. All right? Thus, 1 plus the square root of minus 3 divides 2 times 2. Right? Yet, 1 plus the square root of minus 3 does not divide 2. So look at the definition of prime. A is prime if when A divides a product of two things. A is not a unit. First of all, 1 plus the square root of minus 3 is not a unit. I will prove before long. Haven't proved it yet, but it's not. So it's not a unit, and it's equal to the product of 2 and 2, and yet it does not divide either 2 or 2. Okay. Now, I haven't proved that yet. Let's see why. Can we prove that it's not at all obvious, by the way, it's not obvious at all that this is true. You know, why is this true? In fact, there are 3 non-obvious claims on the board at the moment. Why? And I said that this is not a unit. No, none of those 3 things at the moment has really been explained. I'm just claiming them. All right? So let's look at the last thing. Why is it that 1 plus the square root of minus 3 does not divide 2? What would it mean for it to divide 2? That would mean that we could write 1 plus the square root of minus 3 times a plus b times the square root of minus 3 equal to what? Equal to 2. So is it possible to solve that? I mean, can you find? So we're begging this question, okay? What does that mean? That means that a minus 3b plus, let's see here, a plus b times the square root of minus 3 is equal to 2. Can we solve these equations? So what is this equation? What does this tell us? It tells us 2 things, right? It tells us that a minus 3b is equal to 2, and it also tells us that a plus b is equal to 0. Here I'm using the rational independence of 1 and the square root of minus 3. In other words, there's no rational multiple. Well, integer linear independence, if you, well, whatever you want to call it. The point is, if you have an equation like this, you can equate the part which is not next to the square root of an irrational. Excuse me. The thing that is not irrational, this piece, the real piece, if you will. Oh, forget about all that. Let's be easier. This is complex, right? We know that the real part has to match the real part, and the imaginary part has to match the imaginary part, right? So the real part, a minus 3b equals to 2. The imaginary part would be, well, I mean, if you want me to, even fine, it's I times square root of 3 times a plus b, if you like. There's the imaginary part, right? If you want me to fall back on complex analysis, we could do that. Then that's got to be 0. So we divide by square root of 3, we just get a plus b is 0. But there's a more general result, guys. If d is square free, if you have something like blah plus yada, square root of d is square free, is equal to blah prime plus yada prime square root of d, it follows that blah is equal to blah prime and yada is equal to yada prime. if we're working in Z adjoins square root of D, or if we're working in Q adjoins square root of D. The point is the square root of D is not a rational number, so these are independent. Okay, just a point of order. This may be an important insight to give you as you work on different problems in the homework and so forth, right? So let me erase that from the record. There we go. Okay, so continuing, we've got B is equal to minus A, right? And then if you go put that up in here, we get that 4A is equal to 2. Right? Now that is a very hard equation to solve using integers. Right? That would say A is equal to a half, which would be, is no allowed. Yes, it's not allowed. Therefore, 1 plus the square root of minus 3 does not divide 2. And since it's also not a unit, that shows you that it is, in fact, not prime. Right? So it's not a unit, and it does not satisfy the needed condition to be prime. So here we have an example of an element which is irreducible, but is not prime. Now, if you think about it, have you guys, in your algebraic education, some of you have had college algebra here, someplace other, different places. If you look at different college algebra books, you'll find different ones that refer to polynomials which cannot be factored. Some college algebra books will refer to them as irreducible polynomials. There are other college algebra books that will refer to them as prime polynomials. Right? So, from a more sophisticated viewpoint, this is kind of a dangerous idea because there's a distinction between prime and irreducible. But guess what? In the context of those algebra books, these are equivalent concepts. That's what we're going to show today. But not always, as we've just seen. Yeah. So when is prime the same as irreducible? When is it not? All right? So the next big tool for us, which is super useful, is the idea of a norm. Let R be an integral domain. Any function n that maps the ring, the integral domain, to the natural numbers union with 0 with n of 0 equals to 0 is called a norm if it's called a norm on R if, first of all, the norm of A is greater than 0 for A not equal to 0. Oh, I'm an idiot. I can't read my own writing. Actually, there was a period after that. It's called the norm on R, period. Capital if. If n of A is positive for A not equal to 0, then it's said to be a positive norm. If n of AB is equal to n of A, n of B, then n is said to be a what? Blank norm. Fill in the blank for me. What would that property probably be called for a norm? What do you guys think? No? All right, fine. I guess I have to do everything in here. Multiplicative. I don't know. I don't think it's that surprising. It preserves multiplication, right? All right. So a principal one we're interested in, there's a few different ones we're interested in actually, but well, Let's focus on what I'm interested in. Z adjoin the square root of D, where D is square free. We can let the norm of A plus B times the square root of D be equal to A squared minus DB squared. Now, let me kind of explain to you why we would do that. The basic idea, I mean, that's the definition above, but it stems from this algebra here, right? So if we have A plus B times the square root of D, and we multiply it by A minus B square root of D, what do we get? Oh, we get exactly what we have above, okay? Because the BA square root of D and the minus AB square root of D cancel out, and it just leaves you that much. So if I'm willing to say, you know, definition A plus B square root of D star equals to A minus B square root of D, all right? Now, okay, if D is negative, that is, honest to goodness, complex conjugation. But D doesn't have to be negative. So this is not always complex conjugation. It could be something else that we don't really have a name for. But it's, well, it's the rational conjugation in some sense. The thing we did to rationalize, to bring square roots out of denominators back in the day, yeah? And the thing is that this star has the following properties. WZ star is in fact equal to Z star W star. And also, if we take a sum, you know, we get this as well. You can easily check these properties for this generalized complex conjugation, if you will. And so what I'm really saying is that the norm of Z is equal to what? ZZ star, right? So in some sense, this norm is like the squared modulus. Yeah. Go for it. This is not complex conjugation. I will try to use bars for complex conjugation. I will try to use bars for complex conjugation, but there are places where I forgot. So you're going to have to understand in terms of context, generally speaking. If ever in doubt, ask me, and I'll try to settle that. It's a quirk of my upbringing. I was raised by physicists, and they use stars a lot of times. And then mathematicians tend to use bars. And then I'm somewhere in the middle. So, not that my parents were physicists, it's just my my education was. My parents are doctors, right?
My parents are physicists.
There you go. So you were actually raised by physicists, like literally. That's good. See, you should study physics, then you could be a second generation physicist. You're good? Okay. Well, it's good that you didn't choose physics as a major here, you know. You wouldn't be here. Oops. Anyway, before I say something I have to edit. Was that something I have to edit? I don't know. It's a meta-editing questions. The point is, now you should first of all, I was hoping that the question would be, hey, this doesn't match the norm I saw in linear algebra, to which I'd say, yes, you're right. It's not a norm in the sense of linear algebra. This is a wholly different usage of the term, right? Much like a societal norm does not satisfy the 4 axioms that we learned in linear algebra, right? But this norm is in fact multiplicative, right? It is multiplicative. It does satisfy these these are properties of the thing building the norm. I would say that in the case that D is imaginary, this norm is the modulus squared. All right. In the case that D is negative, then we're actually looking at the norm being the modulus squared. You're like, okay, well, this is great, but what on earth does this have to do with associates, irreducible, and prime, right? Well, let me show you. Oh, my bad. I was missing a very important thing, which is, what am I missing? I'm missing this. I'm supposed to take the absolute value of that. Sorry about that. That doesn't matter. That doesn't really, I don't think it matters in the case that, listen, in the case that D is negative, that doesn't matter because it's the modulus squared, which we know is non-negative, right? But in the case that D was positive, that kind of ring, we need the absolute value. All right, theorem. Properties of this norm. One, we have that the norm of x is equal to 0 if and only if x equals to 0. Two, we have that the norm of xy is equal to the norm of x times the norm of y, right? For all x, y, and z adjoin square root of d. Three, we have that x, an element of z adjoin the square root of d, is a unit if and only if n of x is equal to 1. Well, that's really nice. And then 4, we have that if n of x is prime, then x is irreducible in z adjoin square root of d. So these are properties of this norm I've just introduced, which are quite wonderful. Yes?
So when you put the absolute value on the top, does the one on the bottom get that too, or is it still?
Yeah, it needs that too, unless, of course, you're right, yeah. Absolutely. Yeah, absolutely. The best puns are the unintended ones. All right. Okay. So, we could prove this theorem. Let me attempt to prove 4. All right, so maybe I can prove 4 and 3. N of x is prime. So x is irreducible. Consider x equals to ab for x, a, and b in z adjoin square root of d, okay? Then the norm of x is equal to the norm of a times the norm of b, right? If n of x is prime, then by Euclid's lemma, right? Either, let me call this prime p. P divides n of a. Well, wait a minute. If n of x is prime, then p divides n of a or p divides n of b, but not both, right? Well, how can I say it? That means this is a stupid way of saying it. What's a better way of saying it? If P is prime, what does that say about n of A, n of B? Forget Euclid's lemma. Then what? N of A is unit, or n of B, not a unit either, is 1, or n of B is 1, right? If it's a prime and we have a factorization of a prime, then one of the factors is 1, because we're talking about a positive factorization here, right? Because we put the absolute values on it. So we've got product of positive numbers, one of it is equal to a prime, so the numbers, one or the other of them is 1. So then, which implies that A is unit, or B is unit by part 3, right? Which we haven't proved yet, but we will soon. What does that say? It says if we have a product, if we have a factorization of x, then one or other of the, at least one of the factors is a unit, right? Which proves that x is irreducible. So prime norm implies irreducible element. Now to prove 3, how will we do that? What are we supposed to do? A unit, right? X in Z adjoins square root of D, a unit, implies what? So if we let x equals to, let's say, a plus b square root of d, there exists what? C plus d squared of d, right? Oh, bad choice. I better use other letters. Let's say alpha plus beta square root of d. Let's call this thing y, such that what? Such that xy equals to 1, right? That's what it means for it to be a unit. But the norm of xy is equal to the norm of x times the norm of y, which is equal to the norm of 1, which is equal to what? Well, that's 1. So we have the product of two integers, positive integers, is equal to 1. What does that say about these integers? That they're both 1. As you can see, I actually did not even need to get into these details, right? These details were really irrelevant to this proof, weren't they? I had in my mind something more technical and awful to get into, and I'm glad we didn't need to. Yay! So there's the proof of 3, which then gives us 4. Now let's apply these back to my original example. All right? So let's look at, so let's use the norm on our example of z adjoin the square root of minus 3. So first of all, check out what's the norm of 1 plus the square root of minus 3. So we're supposed to do 1 plus the square root of minus 3 times 1 minus the square root of minus. I mean, you can do this different ways. Take the absolute value of that, yeah? So that's 1 minus 3. So I think that the norm is 4, isn't it? Yeah. So this is not equal to 1, right? So therefore, 1 plus the square root of minus 3, not a unit in Z adjoin the square root of minus 3. These rings, actually, of algebraic integers, as they're called, Z adjoin the square root of minus 3 or minus 5 or other things like this, they've got kind of interesting sets of units. We'll see as we go on in here. There's usually a finite number of units. So these are rings with tons and tons of things that are not units. Yeah.
So I just want to clarify. So the definition of prime, that's so if A divides BC, A has to divide B or C for all possible. Like you take 4, A does divide 4 in our example over here, but it doesn't divide 2, and that's why it's not prime. It has to
Right.
It has to divide all factors, like at least one of the factors.
If there exists a pair, BC, such that A divides the product BC, and yet A divides neither B nor C, then it's not prime. Yeah. It just happens that the factor 2 times 2, made the process of deciding whether it divides B or C a little bit, just one job rather than 2. Okay, so it's not a unit, check. And what was the other claim? Irreducible. So what's the norm? Uh-oh. Sorry. Now all of a sudden I'm... Oh. Okay, so to see it's not irreducible, we need to do some more calculation. Suppose 1 plus the square root of minus 3 is equal to xy, right? To prove it's irreducible, we need to show what? Either x or y must be a unit, right? So let's see here. The norm of 1 plus the square root of minus 3 is equal to 4, as we've just argued. That has to be equal to the norm of x times the norm of y. Right? So then what? I said, so let's try to eliminate the case that we're worried about, which would be what? If they're a unit, they have a norm of what? 1. So we're trying to get 4. How can you get 4 as a product of integers? 1 times 4, 4 times 1, 2 times 2? I'm right? I worry. My ability to do combinatorics, not awesome. You've seen it. So 2 times 2 is the thing we need to worry about, right? If we could have norm of x be 2 and norm of y be 2, that would mean that there's a factorization. There's probably an underlying factorization which would prove that it's reducible, right? So what would the norm of x, so if x equals to a plus b times the square root of minus d, then what's the norm of x? Well, the norm of x is equal to a squared minus, well, d here is what? 3, right? So minus 3b squared, and that would have to be equal to 2. Okay? Oh, I'm an idiot. Is it minus? It's plus, right? Plus. It's minus db squared, but d is minus 3, so that gives me plus 3b squared. So there you go. We have that. And then the question is, can you solve that? Right? Do there exist a and b? I said d is equal to 3, but I should say d is equal to 3. I put the minus here, yes. Fine. Square root of d with d equals to minus 3 is what you're about to ask me about, right? Okay, there we go. Sorry, I can't make up my mind whether I'm writing, the saying d is 3 with a minus, or saying d is equal to minus 3. Thank you. So here a and b, if this is going to be a interesting problematic reduction of 1 plus the square root of minus 3, then we'd need a and b to be what? Integers, yeah? Can you find an integer solution to this equation? Yeah? Well, if we put b equals to 0, that's kind of our only hope, right? Because if we have b non-zero, then we've got something larger than 2 here. So if b is equal to 0, that's our only hope. And b equal to 0 gives me a squared equals to 2, which has no integer solutions. So there's no such solutions. Therefore, there are no such x and y. Consequently, this is an irreducible element. So it's not a hard argument to see it's irreducible once you have this norm in hand. Now, sometimes you have to think harder. The one I'm about to show you, let's see here. Come on. Come on. There we go. So we just got done working through example 4.76. 4.77 is kind of a little bit different. Here we look at 7 in z adjoining the square root of 5. Suppose 7 was equal to x times y. Then the norm of 7 would be 49, right? And the question I'm asking is, you know, is 7 irreducible, right? Well, if it is, then we can find x and y such that 49 is equal to the norm of x times the norm of y. And we want neither x nor y to be units, so that means that we need both of these to be 7, right? So then we're looking to solve 7 is equal to the absolute value of a squared minus 5b squared in this context, right? Or if you prefer, a squared minus 5b squared is plus or minus 7. Well, a convenient way to analyze that equation is to work mod 7. See, mod 7, we're trying to solve a squared minus 5b squared equal to 0. And so you can explicit checking of possible solutions. In other words, sorting through 49 possibilities. Yeah, because these 7, A and B, 7 choices, 7 times 7, 49 possibles. If you work through it, though, the only thing that works is A and B both 0. Consequently, 7 divides A, 7 divides B, which means that A squared minus 5B squared is divisible by 49, right? Because 49 divides A squared, 49 divides B squared, so it divides the difference of these two things. Yet, A squared minus 5B squared is equal to 7, which is not divisible by 49, so no solution. Okay. So just because then, I mean, there's harder examples is my point. I've spent entirely too long on the numerical part today. I really should spend time on these theorems. For now, I'm just going to have to state them since we're almost out of time, all right? But here it is. In an integral domain, every prime is an irreducible, all right? In an integral domain, every prime is an irreducible, right? What did the example up on the board show? This is an integral domain, right? This is what? This is an irreducible, which is what? Not prime. It's not if and only if. This example shows that. But this calculation right here, this proof, proves that prime implies irreducible. Let me just take a minute to work through this proof at least. So if A is a prime in an integral domain, if A is equal to xy, then as A is prime, we either have A divides x or A divides y, right? Now if A divides x, that means x is equal to AB. So we can look at x times 1, which is equal to x, which is equal to AB. And then where's this xy coming from? Remember, A is equal to xy, so I expanded A back into xy again, which is equal to xyb. Then I said that this equation implies that 1 is equal to yb. How can I do that? Why does this equal to that imply 1 equals to yb? What's our context? It's an integral domain which has the cancellation property, right? So by the cancellation property of an integral domain, I get 1 equals to yb, which says that y is a unit, right? And similar argument can show that in the case that x is a unit, A divides y, and this implies that x is going to be. In the other, if you do go through the other, if you suppose that, excuse me, words. Similar, like I said, similar arguments show x is a unit in the case that A divides y. So I'm looking at the case A divides x, right? If we sort it through A divides y, almost the same argument will show that x is a unit, I believe. So in either case, we either have x or y as a unit, which then gives us that that gives us that the A we're looking at is an irreducible. So in short, prime implies irreducible in an integral domain. Another interesting task, another interesting theorem, which I should prove in detail in a future lecture, is this. If we have the principal ideals generated by A and B are equal in the context of an integral, a commutative ring with identity, then it follows, well, if in addition, if that's an integral domain, then if we look at the principal ideal generated by A, and we have the principal ideal, if we have I is also generated by B, then A and B have to be associates. So the interesting role that associates play is if you give me a principal ideal generated by A, and I want to know, okay, what other elements in the ring could be used to generate that principal ideal, the answer is associates of the given generator. How many associates are there to a given generator depends on how many units you have in the ring. The more units you have, the more you can take a given generator and change it to a different known associates, right? So. The proof is not hard, we just don't have time at the moment, guys. And then my punchline for today is if we're in a PID, a principal ideal domain, then an element is prime if and only if it's irreducible. So principal ideal domain is an integral domain in which every ideal is principal, right? So we already know what? We already know that prime, no, excuse me, we already know, I've already forgotten. We already know what? Prime implies irreducible, but the converse direction is also true if we're in a PID. And again, the proof is not hard, but it's going to take me about 10 minutes of class to work through. So it's probably going to take me about a half hour to prove both of these, which means I probably need to make a video. And let's see here. And that's pretty much it for this lecture. I'm just about 20 minutes of proofs behind, so sorry. You can hit it.